Azimuthal quantum number. This quantum number was proposed by Sommerfeld to explain the fine lines of the spectra. We have already discussed about the fine lines of the spectra in Azimuthal, Sommerfeld's atomic theory. That means when a spectra was recorded with a powerful spectroscope, the lines in the hydrogen spectra, which we feel it as a single line, is found to be a group of lines. That spectra is said to be fine lines of the spectra. So to explain that fine lines of the spectra, Sommerfeld proposed this quantum number, which is known as azimuthal quantum number. This azimuthal quantum number will give us the information regarding the sub-energy levels that are present in each main energy level. Bohr is concentrated only on main energy levels. He has no idea regarding the sub-energy levels that were present in the main energy level. But Sommerfeld is proposing that each main energy level will have some sub-energy levels, and those sub-energy levels, the number of sub-energy levels that were present in main energy level are equal to its n value. That is, for example, if this is the nucleus, from the nucleus you have first energy level. For this energy level, n is equal to 1, and from a certain distance from the first energy level you have another energy level, that is n is equal to 2, and some other energy level n is equal to 3, some other energy level n is equal to 4, and so on. Now what Sommerfeld is proposing, this was the proposal of Bohr. At a specific distance from the nucleus we have some energy levels. Now what Sommerfeld is proposing, each main energy level will have some sub-energy levels. The number of sub-energy levels that were present in a given main energy level will be equal to n. So here for n is equal to 1, only one sub-energy level is there, so it is said to be L, and its value is 0. In second main energy level, you have two sub-energy levels. For one, L is equal to 0. The second one, it is 1. In third energy level, you have three sub-energy levels. They are L is equal to 0, L is equal to 1, L is equal to 2. Three sub-energy levels are there in the third main energy level. In fourth energy level, you have four sub-energy levels. They are L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. So this azimuthal quantum number will give us the information regarding the sub-energy level to which this electron belongs. In first energy level you have L is equal to 0, that is S sub-energy level. In second energy level you have two sub-energy level, S and P. In third energy level you have three sub-energy levels, S, P, D. In fourth energy level you have four sub-energy levels, S, P, D, and F. So the number of sub-energy levels that were present in a given main energy level will be equal to its n value. And their values are from 0 to n minus 1. So here n is equal to 1, L is equal to 0. N is equal to 2. L values are two values. They are L is equal to 0 and L is equal to 1. L is equal to 1 means N is equal to 2 minus 1 is equal to 1. And for third energy level, you have 3 L values, 0, 1, 2. This 2 is 3 minus 1, 2. In fourth energy level, you have 4 sub-energy levels, 0, 1, 2, 3. 3, 4, 4 minus 1, 3. So, in each, there are main energy levels. N is equal to 1, N is equal to 2, N is equal to 3, N is equal to 4. In first energy level, you have one sub-energy level. For it, L is equal to 0. For second energy level, you have two L values. They are L is equal to 0, L is equal to 1. For third energy level, you have three sub-energy levels. There are L is equal to 0, L is equal to 1, L is equal to 2. For fourth energy level, you have 4 sub-energy levels. L is equal to 0, L is equal to 1, L is equal to 2, L is equal to 3. And this quantum number is also called as angular momentum quantum number. This quantum number is also called as angular momentum quantum number. Angular momentum quantum number. This quantum numbers explains the shape of the orbitals. This quantum number explains the shape of the orbitals. If L is equal to 0, the shape of the orbital is spherical. If L is equal to 1, the shape is dumbbell. L is equal to 2, this is double dumbbell. And here you have 3 dumbbells for L is equal to 3. That means it's complicated to explain the shape. The shape is very complicated. That's why it has 6 lobes. So this is regarding the azimuthal quantum number. Azimuthal quantum number. This azimuthal quantum number was proposed by Sommerfeld to explain the fine lines of the spectra. For the fine lines of the spectra. This quantum number is denoted with small l. The values of this quantum number are 0 to n minus 1. This quantum number will give us the information regarding the sub-energy level to which this electron belongs. That means Bohr was mentioned only main energy levels and he designated as its values as n is equal to 1, 2, 3, 4, so on. But Sommerfeld is proposing that in each main energy level, there are some sub-energy levels. Those sub-energy levels are designated as L, small l. And their values are from 0 to n minus 1. First energy level, you will have only one sub-energy level. Its L value is 0. It is spherical in shape. In second energy level, you have 2 sub-energy levels. For one sub-energy level, L is equal to 0, which we call it as S sub-energy level. It is spherical in shape. And second sub-energy level, L value is 1 and it is said to be P sub-energy level and its shape is dumbbell shape. In third main energy level, we have 3 sub-energy levels. They are L is equal to 0, L is equal to 1 and L is equal to 2. L is equal to 0, S sub-energy level. L is equal to 1, P sub-energy level. L is equal to 2, D sub-energy level. That means in third main energy level, we have 3 sub-energy levels, namely S, P, D. In fourth energy level, we have 4 sub-energy levels. Their values are L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to 3. L is equal to 0 is S sub-energy level. L is equal to 1 is P sub-energy level. L is equal to L is equal to 2 is D sub-energy level. L is equal to 3 is F sub-energy level. So, the number of sub-energy levels that were present in a given main energy level are equal to its n value. Suppose if n is equal to 5, there are 5 sub-energy levels. If n is equal to 6, there are 6 sub-energy levels. N is equal to 7, there is possibility for 7 sub-energy levels, and so on. And this quantum number is also called as angular momentum quantum number. And this quantum number will explain us the shape of the orbital. If L is equal to 0, it is spherical in shape. If L is equal to 1, it is dumbbell in shape. If L is equal to 3, it is a double dumbbell shape. And L is equal to 3, that is F orbital. It has a complicated shape like this. Now, the third quantum number is magnetic quantum number. This magnetic quantum number was proposed by Landé to explain Zeeman effect and Stark effect. Now let us recollect what is Zeeman effect and what is Stark effect. The splitting of spectral line when atoms are in magnetic field, that effect is said to be Zeeman effect. And the splitting takes place, the similar splitting takes place when when atoms are kept in electric field, that effect is said to be Stark effect. What is it? Let us see. Now we already discussed that in hydrogen spectra, we find some lines in the hydrogen spectra. When the spectra was recorded with a high resolution spectroscope, these lines are found to be a group of lines. So why these lines are obtaining? Because these lines are obtaining when electron transition takes place from one main energy level to other main energy levels. But within the main energy level, there are some sub-energy levels. So, from the same sub-energy level, the electron transition may occur. That means the electron may jump from 2s to 2p or 2p to 2s, or 3s to 3p, 3p to 3d, or 3d to 3s, or 3s to 3p, or 4s to 4p, 4p to 4d, or 4d to 4s, like that. Within the main energy level, since there are some sub-energy levels, if transition takes place within the main energy level, they will give a separate lines. This is said to be fine lines of the spectra. Fine lines of the spectra. Because in each main energy level, there are some sub-energy levels. There is a difference in the energy between the sub-energy levels, though it is a small difference, but there is a difference of energy. 2s energy is slightly less than 2p energy. 3s energy is slightly less than 3p energy, and 3p energy is less than 3d energy. So within the main energy level, the energy of the sub-energy levels will vary. That's why if you magnifying the spectroscope, you will get a different lines. If you go on increasing the magnifying power of the spectroscope, if high resolution spectroscopes are taken, further division is not observed. But the spectra, this spectra which was recorded here, with the same spectroscope, before taking the spectra, if the atoms are kept in magnetic field or electric field, these fine lines which we observed previously with the same spectroscope, just because of that magnetic field, each line is found to split. Further split. This we call it as splitting of spectral line. Fine lines are differ from the splitting because here this one line is a group of lines, but one line here, same line, but a splitting is observed. That splitting is observed only in the influence or under the influence of electric field or under the influence of magnetic field. The influence of magnetic field was studied by Zeeman, and the influence of electric field was studied by Stark. That's why those effects are named after them as Zeeman effect and Stark effect. This splitting is not because of the resolution of the spectroscope. This is only because of that electric and magnetic fields. It indicates that each sub-energy level, there are certain orbitals. Those orbitals are having same energy. Those orbitals are having same energy. They are at an equal distance from the nucleus. That's why, though we increase the magnifyingness of the spectroscope, that splitting is not occurred. But in the influence of magnetic field or electric field, then only they were split. Why they were split in electric field or magnetic field? We know the properties of a magnet. If you bring one magnet to another magnet, deflection will take place. Because if you take a magnet, it will show to north and south. If I bring another magnet to this magnet, a reflection will observed. That means same poles will repel or opposite poles will attract. So because of this attractive or repulsive forces, some deflection is observed. So previously, for example, in L is equal to 1 sub-energy level, there are some orbitals. All orbitals are same energy. That's why this looks like 1. But if we bring a magnet here, some orbitals will reflect this side and some orbitals will reflect this side, so that all the three will give 3 different lines. This we call it as splitting of spectral lines. This splitting was occurred because each electron which is revolving in a circular path or elliptical path will behave just like a small magnet. When another magnet bring or nearer to this, it will repel or attract. So because of the spinning directions, there are different directions, spinning directions. That's why each magnet will have a different poles on it. So that's why that reflection is occurred. Due to that, different orbitals are found in each sub-energy level. The number of orbitals that were present in each sub-energy level are equal to 2L plus 1. The number of orbitals that were present in each sub-energy level will be equal to its 2L plus 1 value. For example, if L is equal to 0, the number of sub-energy levels are 2 into 0 plus 1, that is equal to 1. And these sub-energy levels are designated with M, so its value is M is equal 0. For L is equal to 1, the number of sub-energy levels are 2L plus 1, that is 2 into 1 plus 1, that is 3. So L is equal to 1, that is P sub-energy level. It has 3 orbitals. They are Px, Py, and Pz. Px, Py, Pz. So their values are M is equal to minus 1, M is equal to plus 1, and M is equal to 0. Px, Py, Pz. If L value is 2, it will have 2 into 2 plus 1, that is 5 orbitals. That means in d subenergy level, you have 5 orbitals. They are d xy, d yz, d zx, d x square minus y square, and d z square. And their m values are m is equal to minus 2, m is equal to minus 1, m is equal to 0, m is equal to plus 2, m is equal to plus 1. So 5 values are like that. Similarly, if L is equal to 3, we have 2 into 3 plus 1, that is equal to 7 subenergy levels. So, this is regarding magnetic quantum number. Magnetic quantum number. This magnetic quantum number was proposed by Landé to explain Zeeman effect and Stark effect. Quantum number was denoted with small m. This explains the orientation of orbitals or spatial arrangement of orbitals in an atom. So this quantum number is also called as orientation quantum number. The other name for magnetic quantum number is orientation quantum number. This quantum number is denoted with small m. The small m values are from minus L to plus L, including 0. That means if L is equal to 0, m will have only one value, that is m is equal to 0. If L is equal to 1, m will have 3 values. They are m is equal to minus 1, m is equal to plus 1, m is equal to 0. If L is equal to 2, m will have 5 values. They are m is equal to plus 2, m is equal to plus 1, m is equal to 0, m is equal to minus 1, m is equal to minus 2. If L is equal to 3, m will have 7 values. They are m is equal to minus 3, m is equal to minus 2, m is equal to minus 1, m is equal to 0, m is equal to plus 1, m is equal to plus 2, and m is equal to plus 3. This is regarding magnetic quantum number. This quantum number gives us the information in a given subenergy level in which orbital the electron is present. In which orbital. N value gives us information regarding the main energy level in which the electron is present. L value gives us the information in the given main energy level in which subenergy level the electron is present. And this magnetic quantum number will give us in which main energy level, in which subenergy level, and in that subenergy level, in which orbital the electron is present. That's why I am saying that these quantum numbers are nothing but the address of an electron in an atom. We know that the person belongs to which country, in that country, which state, in that state, which district, in that district, which town, in that town, which street, in that street, which house. Just like that, here to which main energy level, in that main energy level, to which subenergy level, in that subenergy level, which orbital that particular electron belongs. And the fourth quantum number is spin quantum number. Spin quantum number. This quantum number was proposed by Welbeck and Gaudsmith to explain the spinning direction of the electron in an atom. We know that electron will revolve in its own axis, that we call it as a spinning on its own axis and revolving round the nucleus. For spinning direction, there are two possible directions, this direction or this direction. So this direction we call it as clockwise direction, and this direction we call it as anti-clockwise direction. Only two possible directions are there. That's why in any orbital, there is possibility for two electrons only, because only two spinning directions are there. The electron can spin only, in an orbital can accommodate only two electrons. In that orbital, one electron will spin on clockwise direction and other electron will spin an anti-clockwise direction. So this quantum number will have only two possible values. They are plus half and minus half. S values are plus 1 by 2 or minus 1 by 2. Each orbital, there is possibility for only two electrons, because there are only two possible directions for a spinning. One is clockwise spinning, another one is anti-clockwise spinning. That's why in any given orbital, there is a place only for two electrons. If one electron spins on clockwise direction and other electron will spinning in anti-clockwise direction, so the magnetic field that was produced by one electron is neutralized by other electron, and the resulting magnetic field will become 0. So the values for this quantum number are plus half and minus half. Plus half and minus half, spin quantum value. This quantum number was proposed by Welbeck and Gaudsmith. It gives us the information regarding the spinning direction of an electron. For a spinning, only two possible directions are there. One is clockwise spinning and other one is anti-clockwise spinning. So one orbital can accommodate only two electrons, one with clockwise spin and other with anti-clockwise spin. That's why it has only two values. Possible values are only two. One is plus half and other one is minus half. So here we have four quantum numbers: N, L, M and S. So with the help of these quantum values, you can identify an electron in an atom. These four are the address tags for an electron. Address tags for an electron. In which main energy level? In that main energy, in which sub-energy level? In that sub-energy, in which orbital? In that orbital, in which direction that electron is spinning? With the help of this, we can estimate the position of electron in an atom. These four quantum numbers are required to explain the particular electron. Suppose if you give all these four quantum numbers, then only you can identify with that particular electron. For example, if you just I say so and so person, where he lives, nobody can say. If you simply say in Vijayawada, it's not fine because it's a larger city. So to identify a person, we require the 7 tags: name, house number, street, town, district, state, country. Then only we can identify that particular person. Just like that, for an electron with a single quantum number, it is not possible to identify electron. If you give all 4 values for a electron, particular electron, we can easily identify it. So these 4 quantum numbers are nothing but an address for an electron in an atom.